Yep.
Just want to
All
test my
set.
camera and mic. Thanks.
Okay.
Sounds good.
Hey,
Okay. And
uh, hi, Michael. Can you hear me?
Yep, I can hear you well.
I can hear you.
Thank you.
hey, take it away, Michael.
All right. Well, hey everyone. Welcome to the third lightning round talk entitled "Finding, Matching, Classifying." I'm the chair, Michael Stanley. I'm a postdoc at NASA, but contracted through Analytical Mechanics Associates. So I'll, not be talking too much. I'll mostly just be introducing the speakers and fielding questions and things like that. So the way I think we should do this is, we have 35 minutes. It might be easier if we just go through all of the lightning talks, and then at the end we can kind of pool question time. That might just make it easier. So please, write down your questions in the Q&A or to yourself and save them for the end. And then for each of the speakers, if you can stick between 5 and 7 minutes, I think that would be great. I'll give you maybe just a brief tap at 6 minutes, just to make sure that you know how much time you have left. And I think that should be it. Okay, so first we have Somadeep Bhaumik. He is from University of Maryland, and he'll be giving a talk titled Matching Legacy Time Series Models with Implied Marginals of Multivariate Models. So with that, feel free to share your screen, Somadeep, and take it away. Great, I can see your screen. But you are muted.
Okay. You can hear me now, right?
Yes, loud and clear. Take it away.
Thank you so much. Hello, everyone. My name is Shomadip Bhaumik. I'm second-year grad student at the Department of Math and Stat at UMBC. So today I'll be talking about reconciling legacy time series models with implied marginals from multivariate models. So this is a joint work with Dr. James Lipsey and Dr. Anindo Roy. So let's talk about the problem at hand. So government agencies often require to update time series data. There might be some new surveys, some additional indicators, or a change in the statistical pipeline. And this demands a shift from the univariate modeling to multivariate joint modeling. But these transitions are not easy. There might be some loss in the historical continuity, or it might have to neglect some high precision legacy model or huge amount of training data. And that leads us to an important question. Can we model the multivariate time series data while incorporating the univariate legacy series? Now, here is a toy example of what I'm talking about. So as you can see, the blue series has been observed for quite a long period, and from the 100 time point, the agency started recording two other series, and they decided to model all of them jointly. So the question is, can we model them jointly while incorporating the legacy model coming from the earlier time points? Now, what does that mean in terms of estimation? So if I want to put it very vaguely, then we want to estimate the multivariate model parameters such that the univariate marginal of the legacy component stay close to the legacy model. Now, the univariate information can be available as a historical time series data or an appropriate univariate model, or maybe both. But what will be our approach? So we will incorporate a penalty in our model fitting, and the penalty would be the discrepancy between the legacy and the implied marginal model of the legacy component. Now let's try to formalize this thing. So for now, our k-variate time series comes from a causal verb P, and we will utilize the final equation form to get hold of the implied univariate marginal process. Now each component from the var will have an implied ARMA P star Q star model, where P star has an upper bound P times K and the Q star has an upper bound P times K minus 1. Now the AI polynomial will be same for each component, and for the MA part, we need to calculate the SEVF and do spectral factorization to get the MA polynomial. So the implied model for the jth component will look something like this. Now next is the estimation part. So if we for a moment forget about the legacy thing, then what we generally do for maximum likelihood estimation. So we take the negative log likelihood of the VARP model and we minimize it with respect to the model parameter, right? So here we will put a constraint with respect to the divergence between the legacy ARMA model and corresponding implied ARMA model and minimize this penalized objective function to get hold of the estimate of the VAR parameter. Now, specifically, in our project, we will be using the squared distance between the SCBF sequence of the legacy ARMA and the SCBF sequence of the implied ARMA as our penalty. Now, the next important question is, how do we determine the penalty parameter lambda from the data itself? So while doing the penalized estimation, we do not want to deviate too much from the unpenalized MLEs for the remaining components, right? So we have to strike a balance and we want to select the penalty parameter such that the balance is there. And how do we ensure that? We calculate the SCBF sequence of the implied marginals for each component. Then we fix a tolerance level epsilon, and then we identify a set of lambda such that the average squared distance between the SCBF sequence coming from the unpenalized MLEs and the SCBF sequence coming from the lambda penalized MLE across all the non-legacy components is less than the tolerance level. And we take the maximum of that selected set of penalty parameters. That's our penalty, that's our selected penalty parameter. So now time for simulation. We simulate from a 3-variate VAR1 model with this parameter structure. We have 500 legacy time points and 100 time points for which we want to perform the joint modeling. And the implied ARMA model looks something like this. So now we fix 3 different tolerance levels, and increasing the value of the tolerance means we can consider larger values of the penalty parameter. So as the value of tolerance increase, you can see in the legacy component, so the SCBF sequence gradually drifts towards the legacy SCBFs, which we want. And whereas for the other components, it starts drifting away from the SCBF sequence corresponding to the unpenalized MLEs. Now, we do this for 100 times to get the Monte Carlo estimates. And as you can see that as the tolerance increase, the RMSE between the estimated SCBF sequence and the legacy SCBF keep decreasing, whereas for the other component, the RMSE between the estimated SCBF and the unpenalized SCBF keeps increasing. Now, to wrap up, so we introduced a framework within the ARMA-VARMA model class for incorporating legacy information about univariate component time series into multivariate models. We also discussed a possible approach for selecting the penalty parameter, but eventually it totally makes sense to entirely shift to the multivariate paradigm where there is enough data available, but our work might help to avoid a drastic change in the modeling and work as the intermediate steps. So in the future, we'd like to extend this framework beyond the ARMA-VARMA class to a more general class of models. And that's all from me. Thank you so much for listening. And if you have any questions and if you're interested, you can contact me in this email. Thank you again.
Great. Thank you so much for the talk. Very interesting. Okay, as we're transitioning over to Benjamin Raymond, I'll just maybe introduce you real quick. So Benjamin's joining us from the Bureau of Labor Statistics and is giving a talk titled, well, it's slightly different on my document here, so I'll just read your title, Monthly Quarterly SOI Estimates with Bootstrap Standard Error. So Ben, take it away.
Sounds good. Thanks for having me. I'm going to hop right into it. Standard disclaimer, nothing I say here is necessarily a review of the Bureau of Labor Statistics or the Department of Labor. And these are experimental estimates. They're not reflective of things that are planned to be published in any way. And everything's been reviewed for disclosure. So with that, we're off. So here's the idea. Like, what are we doing currently with what we do now is we publish annual or biennial estimates of like workplace injuries and illnesses, not just estimates of counts, but also sort of rates, so injuries per hours. And the idea is like, can we get a finer estimate of this? Can we get something at like the monthly or quarterly level? And that's sort of what was the start for this project. So we're using data from what we call the SOI, the Survey of Occupational Injuries and Illnesses, and that's going to give us our injuries for the numerator of this injuries per hour, and then we're going to end up using the current population survey that takes place on a monthly basis to give us hours at the monthly level. And it turns out that for a subset of the files, we have detailed case data that have dates associated with injuries. And so, long story short, what we can do is we can look at the dates for which we're gathering hours information and the CPS, and we can restrict our sample to be match to have the injuries and illnesses that occur during those same dates that we have the hours. So what we can do for each month is we can get the hours from the CPS, and then we can restrict our source sample to get the injuries that correspond to that same week we get the hours from. So we can get some sort of finer estimate there. So that's the idea, right? And so you can get something like this where I'm showing you, I put artificial gaps between years so you can better see the seasonal pattern within a year. But I'm showing you each point on this graph is a year-month combo. So like January 2009, February 2009, etc. And I'm showing you like basically the injuries per hour rate per 10,000 full-time workers. You can see there's quite a bit of seasonal variation. So the blue is just what we publish publicly on an annual basis. And the orange is the experimental series if we were going to do something at a monthly level. So you can see there's quite a bit of variation there that you would not get from just looking at the monthly series or the annual series. So the question is then we can do that, great. Are we done? No, there's some question about precision with the estimates, right? We want some idea of how confident we should be in these estimates. So what are we going to do? We're going to do some bootstrapping. I'm not going to get too much into details. I'm trying to give you guys just a general overview, but essentially bootstrapping with some bias correction, and then we're going to follow some of the guidelines put forth in Kalanikov's 2010 paper, working with complex surveys. And so the basic idea is we're going to mimic the survey design within the bootstrapping procedure. So every time we sample a bootstrap sample for an iteration, we're going to then, using that sample, recalculate all the weights and try to mimic like the complex survey design that went into gathering the original data. And that's going to be used to get our bootstrap samples, which will then help us make our standard errors and some confidence intervals as well. So that's the main idea. And so I am just here to now show you a bit about what we can do. So with that in mind, I'm just showing you here, same idea, same graph as before. The only difference is we're now looking at, we can actually see what the resulting we're using here percentile bootstrap confidence intervals. We're playing around with a couple of different others to see what works best. But you can see like we're able to actually get some fairly decent precision on these estimates. And a lot of the seasonal variation is quite distinct. So we can do this at the total monthly level. We can also, aggregate this up and do this at the quarterly level. So this is the same kind of graph, except we're just showing you now, quarters instead of months. And then we also in the data, we're fortunate to have some information on like case and demographics and and industry and occupation. So we can do things like it's pretty thin because we have to restrict the data quite a bit to match up with the CPS reference weeks. So we can't. It's very rare to be able to get more precise than like a 2-digit industry code, but still, that's something we didn't have before potentially that could be very useful. And you can see like series differ in their patterns, like even series that were maybe similar or close have different responses to say COVID in 2020 are affected in different ways. And not just different in terms of levels, but different in terms of like when you're seeing spikes throughout the year. Same thing with like occupation, nothing different there in principle. Same with like if you're looking at different demographic characteristics. So you could do this by sex, age. We have race variables too. There are other things you can consider. It comes down to a bit about data thinness depending on what you're looking at. We could theoretically do it for some states, but as you can imagine, we run into some data thinness issues as we maybe deal with some smaller states. So that's something we're thinking about as well. And then finally, we have our own injury classification system called OICS, the Occupational Illness and Injuries Classification System. So we have like injury codes. Not only do we see that injury occurred, there's a code for the injury. We can see like, oh, you burned your hand, or oh, you broke your arm, whatever it might be. And so we can, by type of injury, we can also get these estimates. So That's basically what we're doing. Gave you a taste, idea. If you want to know more, please reach out. Feel free to contact me. Happy to discuss more. So here's my contact info. Thank you.
Excellent. Thank you, Ben. Appreciate the talk. Okay. So next we have Nathan Welch from MITRE. Nathan, if you be able to put your slides up, I'll read the title as you're doing that. So Nathan will be giving a talk titled Bayesian Person-Place Model, Probabilistic Address Imputation from Administrative Records. Take it away, Nathan.
Yes, thank you. So, like everyone else, the views and information here reflect my own opinions and don't necessarily reflect anything about MITRE or its sponsors. What I want to talk about today is work that I've done as part of my PhD research. And really, the goal is to demonstrate that a well-defined person-place model eliminates some limitations of existing methods used by countries around the world that don't have population registers, but want to do address imputation from administrative records. So in terms of methods, existing person-place models used by countries around the world are approximations to a well-defined model. The response variable of interest is a person's administrative record address equals their true address, so it's an indicator. The predictor variables are defined in terms of person level or address level attributes, calculated from the sources themselves, along with the date that an administrative record is filed. And then the training data are survey responses plus the administrative records filed by the same people over the same time frame, all anonymized. So multiple publications have shown that person-place models do work well and have some predictive accuracy, some impressive predictive accuracy, but these performance metrics obscure some key challenges. Most people have just one candidate administrative record address. Some people provide an address that doesn't match any of their administrative records. And all of the PPMs are estimated as if the data are independent binary outcomes. So what the Bayesian person-place model does is formulate the response and predictors in terms of discrete choice model framework. Categorical responses, like the ones that are in this context, are typically modeled with a multinomial distribution, but these distributions have some assumptions about fixed categories where, at an individual level, there's no real categorization of different people's candidate addresses. There's no concept of a red house, blue house, green house across everyone. The other thing is that there are a variable number of candidate houses or addresses that could be assigned. So the discrete choice model framework relaxes this restriction. And the only things that you need to do in order to fit this framework are, one, the alternatives have to be mutually exclusive, the choice set must be exhaustive, and the number of alternatives must be finite. So here's the model formulation. So the response, again, is an individual level for individual I. They can be at either none of the houses, which is indicated by index 0, up to a person-specific number of houses. And this is a vector, a person-specific vector that's also varying with the size of which is also varying with the individual. So this is the main the main innovation or difference from existing models. So I simulated some data and evaluated the performance using several metrics. What I'm showing here in the center are some of the results, with the leftmost column and the top figure being the Bayes PPM probability of matching the true address up to 25 months prior to some target date when you actually want to do something like a simulated census. What I'm showing on the gray lines are the true probabilities and uncertainty intervals. The shaded region shows the Bayes ppm uncertainty level, and then the solid line, color matched line with the shaded region is the Bayes ppm prediction. And then the rows here show the number of candidate addresses. So what we can see is the Bayes ppm recovers both the correct mean and uncertainty around that mean. Whereas if we look at different versions of ppms published, you can see that the uncertainty intervals really are generally not well matched to the true level of uncertainty across time, and the probability, the mean probabilities can be more or less accurate depending on the number of candidate houses or addresses. There are some additional evaluation metrics here that I won't go through in detail, but the main takeaway message that I want to get across is that the Bayes ppm eliminates some key constraints, notably that there's an additional explicit reference to the no match category. The Bayes ppm matches or improves on accuracy of published methods and provides more robust, credible intervals. It's well calibrated and provides interpretable probabilities for research and operational use. And it's a fully probabilistic model that can handle more complex analyses than what's currently possible. There are a few main drawbacks to point out. This is all of these results were generated from simulated data, but there's some variation in the way that administrative records typically flow into statistical organizations, or statistical offices. So that may be difficult to overcome, and that's not accounted for in this assessment. And then population scale data could introduce a computational nightmare. So fitting this model requires an MCMC process or MCMC sampling, which can be prohibitively computationally expensive. So with that, I'll stop and turn it back over.
Excellent. Thank you, Nathan. That's very interesting. Okay. So finally, rounding us out, we have Mark Vanderloo from Statistics Netherlands. And Mark, if you could just go ahead and put your slides up, we'll get started. Okay. And, Mark will be talking about split, apply, combine with dynamic grouping, R package, accumulate. Take it away, Mark.
Yes. Thank you, and thanks for having me in this conference. I've been enjoying it so far. It's my first time, and looking forward to the rest of the conference as well. So today I'm going to be talking about an R package that I released about 2 years ago. And it's a sort of extension of the famous group-wise aggregation, which is, I think, one of the most fundamental data operations that any statistician really uses. I'm sure most people in the audience will be familiar with this picture, but just to get everybody on the same page, because I'm going to extend it a little bit, we start with a data frame, a split, apply, combine paradigm, where we have some value that we want to aggregate over, and we have a categorical variable. We split the data frame according to the values in this categorical variable, and then for each group, we compute some kind of aggregate, and then recombine all the outputs to a nice data frame again. So this is all nice and well, and this is all well supported with packages like dplyr, collapse, data table, poorman. There are many ways to do it, pandas, for example, polars. But in practice, you might encounter some problems. For example, often we use not one, but multiple splitting variables. Now that's usually supported. But especially if you use multiple splitting variables, the groups can become very small. Think about splitting up according to economic activity, region, size class, and maybe some more. And when you have a lot of splitting variables, maybe your groups become so small that you wonder, do I have sufficient support to reliably estimate a mean? Something else that can happen is that maybe you have some data issues in your larger data frame that don't seem so big when you look at the whole data. But once you start splitting things into group, these two missing values here become 2/3 of the group. So you could say that, by splitting data into groups, big data becomes small data, but small problems might become big problems. And so that becomes an issue. And then what subject matter experts often choose to do is something like this. They start writing more complex code where you sort of look at each target group, and if something is bad is happening, the quality of the data in that group is not good enough, we somehow combine groups. And after we've done that sufficient number of times, then we can compute the aggregate. So I've seen code, and then something that seems to be fairly simple, or should be fairly simple, like aggregating according to groups, becomes a very complicated piece of code, because basically the grouping you are applying depends on your data circumstances. And that leads to a lot of things like data lookups, checks, and very involved code that's hard to interpret. And that sort of deters you from the things that you really want to do, aggregate data according to some scheme. And you're focusing on writing complicated, hard to understand code. So on the right, there's one example where there's a NACE classification. That's the European version of the ISIC. The US version would be NAICS, economic classification. And one thing people typically do is like go up in the hierarchy to find like bigger groups to aggregate over. So that's where the accumulate package comes in, is to make that easier. So the accumulate package is basically offers you a formula data interface for collapsing groups under user-defined circumstances. And so here is one function call from the accumulate package that I will just quickly go through so you can see sort of how it works. So of course we have this function called accumulate, and of course we have to input some data. That's just a data frame. In this case, we imagine it has like a 3-digit NACE column, a 4-digit NACE column, so more detailed, a size class, which is also categorical, and a total that we want to aggregate over. So in this case, we would like to have an aggregate on the NACE 4 times size class level, grouped by 2 categorical variables, and we would like to compute the mean. Right, so this is basically split, apply, combine that we have defined right here. Except with this function call from the accumulate package, we can specify a test. For example, we want a minimum of 3 records. Now these tests are completely customizable. You can plug in any type of test you want. You can write your own test function. So it's very flexible, but here we choose to have just a minimum of 3 records. So what will happen is that for each 4-digit NACE size class combination, the algorithm will check whether there are at least 3 records. If so, the average is computed. If not, we take the grouping for that corresponding group. We take the NACE 3 classification times size class. If we have then 3 records, we compute the mean. If not, we fall back to just NACE 3. We basically drop the size class. So that's the formula specification of your collapsing scheme. You start with specifying what you want, and on behind the tilde there are the alternatives, and you can put in as many alternatives as you want. The output is very similar to what you expect from split, apply, combine. You get your 2 output classifications, NACE, 4-digit NACE, and size class. You get your average, and on top of that you get a variable called level that tells you how many steps of collapsing took place in order to compute the average. So this gives you every piece of information that you need to actually interpret the result. So this is the main idea of the package. It basically allows you to specify your collapsing scheme, your alternatives for group aggregation based on local data circumstances that are tested for every group. And of course, what kind of average you compute is completely, or what kind of aggregate you compute is completely customizable as well. You can also compute multiple aggregates. It's very flexible in that sense. So with that, I just want to summarize that the accumulate package, some things that I couldn't show here, but there are 2 functions. One is more resembles the aggregate function from base R. There's a function like accumulate that more resembles the tidyverse, let's say, summary function. You can collapse with a formula interface, but you can also externalize your collapsing scheme using a tabular format. That's what subject matter specialists often resort to when they write this kind of code themselves. And one thing I like to mention is you can also use complex aggregates. So I showed here only an aggregate that results in a number, like an average or variance or something like that. But you can also specify the computation of a linear model or a random forest or whatever, and this will also be stored in the output using lists as columns. If you would like to know more, don't hesitate to contact me. The package is on CRAN, and there's also a paper in the Journal of Statistical Software that was published this year, which gives examples on how to use this in cases of imputation, simple small area estimation, and there's also an analysis of the underlying algorithm. So with this, I'd just like to thank you and maybe very quickly advertise another interesting conference on statistical computing in government circumstances, the use of R in official statistics. If you have a chance, the registration is still open. Thank you.
Excellent. Thank you, Mark. Appreciate that. Okay, well, we still have about 6 minutes for questions, and it looks like Stas had a question for Mark. Stas, would you like to unmute yourself? Actually, I don't know. Can you unmute yourself and ask it, or do I need to do that? Or perhaps you can see that question mark and you can address it directly.
Let's see. Can I see the?
Oh, maybe I have to do answer.
Yeah, I didn't see the Q&A there. Sorry. Is there a functionality to specify which levels can be allowed to be collapsed? Yes, I think the answer to this question, it's a fairly technical question, but I think the answer is yes. Well, not for each group differently. You would have to, no, if you really want a different collapsing scheme for each group, you would have to customize code. Yeah, I think that's the question. Yeah. Yeah, then it becomes more complicated than what can be specified here. Good question.
Great. Thank you for the answer. All right. Do we have any other questions? Feel free to chime in here. Maybe we wait for people to formulate their questions. I had a question for, let's see, for Ben. I was curious if you could maybe say a little bit about how you do the bootstrapping to mimic the survey design. I know it's probably pretty complicated, but maybe just like some broad.
Yeah, I can give you a little overview. So we kind of, there's like two-stage sampling in a sense. So we're sampling from establishments. So we first get like a top line, how many like injuries do you have? But then we do like a subsampling from there. So we say, an establishment might say like, hey, I have, 10 injuries or something. But then we might subsample from those, I guess typically if they say like we have 50 injuries, we'd subsample, I think around like, we used to do like 15-ish. So for 15 of those cases, we see the dates and specifics of the case. What we're doing then in the bootstrapping is saying like, hey, let's select establishments. We're going to cluster sample from those establishments. So we're going to take all, the cases we actually observe, and then we have to adjust, like there's like a subsampling adjustment. There's like a non-response adjustment. There's a couple other adjustments too that we're all doing using the bootstrap sample to recreate all those individual factors to create a new bootstrapped weight for that iteration. And then we're just calculating, we do some like post-stratification things, procedures as well, and then calculate the statistics. So that's the general idea without getting too technical.
Gotcha. No, that's very helpful. Thank you for explaining that. I think we also have another question for you here from anonymous attendee. Let me see. How do you determine whether sufficient bootstrap replicates were used?
Yeah, I mean, so it's an open, I guess it's kind of an open question, right? Because like it's kind of difficult to determine like what the truth is. Like that's a very kind of existential question in many senses. So it's like, So it's something we're looking at. Like, I mean, we try to use a high number, but that's still very much being experimented with. So if you have suggestions, I'd love to hear it. But yeah, figuring out like what the truth is sometimes hard. Often hard.
Gotcha. Great. Okay. I think there's some chat action here. Let me just make sure there are no questions in here. Oh, it looks like Lisa put some links to Mark, I think, some of your material here. So yeah, thanks for that, Lisa. Okay. Well, we still have maybe a few minutes. If anyone has any other questions, feel free to put them in the QA. I also had another question for Nathan, as some other people are maybe thinking. I was curious for your application. Like I liked seeing how the uncertainty bands were kind of better calibrated. I was curious what downstream those are used for. So like what the better calibration maybe help with.
Yeah, so a lot of times, especially for operations, people just take a single number value as like the ground truth, or that is, the state of nature.
Right.
And there have been various attempts to assess like the quality of a ppm probability, again, for operational use. So there's a very natural and long-standing way to measure quality, and that's the level of uncertainty around that estimate. So that's why these intervals are so useful. Another thing that makes these intervals helpful is that if you wanted to do different cuts of subgroups, probability-based analysis, then you can't really use just the single number mean probability from the model. You really need kind of these replicates. So again, like there's much more flexibility offered with more robust probability estimates.
Excellent.
Does that make sense?
Yeah, that makes perfect sense. Thank you for the answer. Okay, well, it looks like that rounds out this session. So thank you again to the speakers. I think all those were super interesting talks. And I think next we have a break until 1:45. So I guess I'll leave it at that, and we'll see you in about 10 minutes. Thanks again, everyone.
Thanks, everybody.
Thanks. Great session.
Thanks, everyone.